3D lighting tutorial part 3. So in this part I'm going to be going over how to use the solver to take our bolts that we had from last time and make them animate in a more interesting way and kind of evolve over time. So just continuing on with the previous scene file, which is available to download. Like, if you don't have it, just check the description. So yeah, basically last time we just had this kind of thing going on. So pretty much these bolts that would like flicker around from spot to spot. They've all got the same kind of like turbulence to them. They're pretty consistent. They've all got the same color. And so adding the solver is going to allow us to do something a little more like this. So just hit W there, and oops, and play this. So here we go. So now you can see, instead of being these consistent, like kind of turbulent bolts, now we've got the bolts that spawn in this kind of like dark purple color, and then over time they kind of evolve, like getting more and more turbulent, and then going through this color gradient of like purple to blue, and then almost to white when they get really turbulent, and then they kind of die. So yep, that's pretty much the lightning solver. So let's dive in here. And the first thing is, I'm just going to kind of like go over basically what the solver does. So if you ever use like a, PopNet, like Pyro, whatever, like they're all solvers obviously. And pretty much the difference between a solver and something like this that we have so far, which is, totally procedural, is that the solver starts at a point in time and then, makes a calculation based on what data exists at that time. So frame 1, there will be like certain data, and then based on that, it will calculate frame 2. Then frame 2, the data is now different, and then it will calculate on that and become frame 3. So you can see if I click around on the time slider here, it pretty much is just going to calculate instantly, like based on whatever frame I click on. And so all that's happening is it's going from the top of the chain and then calculating all the way down to the bottom. And then once it gets to the bottom, it runs a few kind of scripts and some VOPs like based on current frame, and that's what causes it to animate around. But essentially it's making a brand new calculation for every single frame. Like this information has nothing to do with the information on the frame before, right? We've just kind of made the noise change by a tiny increment every single frame, which kind of gives the illusion of animation, even though really it's a brand new calculation on every single frame. And if we just hit D in the network view here, we can go to dependency and show time dependencies. And so that will just give us some glowing green kind of nodes here. And so basically what's going on here is anything that's green is time dependent, or it has a time dependent cook. So these two things up here, the sphere and the grid, like they have to calculate once. So, at the very beginning it goes, here's a sphere, here's a grid, I know what they look like. But then go down to this scatter, now it has an expression here which is based on current frame. So now it knows that it has to re-cook this scatter every single frame. And as a result, anything down the chain below it also is going to have to get re-cooked every single frame. And yeah, so yeah, this stuff, it's time independent. So again, like this stuff gets calculated once and then, it's in memory, like we can scrub around, and only the green stuff has to recalculate. So yeah, that's a bit of a tangent, but it's kind of good to know for optimization. But then the solver, on the other hand, it takes the information that existed one frame ago and then uses that as the basis for the next frame. So yeah, back to the solver. Let's just make a sphere here, and I'll kind of try to show what the solver does. So I'll just look at the sphere, I'll hide everything else, and make a transform. Just put those in. Also, I just found out there's these buttons. You go like, hit those, and it just like lines everything up real nice, which is a fun thing to do. So take our sphere, and I'm just going to offset it. And you don't have to do this, by the way. I'm just kind of like trying to demonstrate the solver. And then we're just going to rotate around the y-axis by 13. Oh no, not 13. Maybe 11 is good. Yeah, 11. So now we have our sphere just traveling in a circle over time. And if I look through the solver, now nothing happens. And the reason for that, if we just take a look at the solver, so it's basically got initial geometry is the first input. I'm just hitting middle mouse key on one of the inputs to see what that input is. You can do that on like any node. So first input is initial geometry, second auxiliary 1, aux2, and aux3. And we can double click to dive inside, and you can see here we've got input 1, 2, 3, 4, and something called previous frame. So the way this works is input 1 is, our circle with the transform, because that was plugged into the first input. So if we look through it now, then we've got our sphere circling around. The previous frame, though, pretty much shows the result of the solver on the previous frame. So pretty much wherever this blue flag is, it's going to show what that blue flag was showing, but one frame ago. So, at the moment, it's not doing anything. And the reason for that is because on frame 1, which is the first frame that it starts calculating, nothing's happened before that. If we go to frame 2, then it's showing what was on frame 1, which is that circle being there. Now if we go up to frame 3, it's going to show what was on frame 2, which is that circle being in the same spot. So 4 is same spot. So pretty much it's just showing the previous frame all the way back to frame 1, so nothing is happening when we have it set up like that. But we can do something. If we merge together, so input 1 is the current frame, that's the sphere spinning around, and then we merge that with the previous frame. And remember, the previous frame shows the result of the whole solver. So wherever this blue flag is looking, so at the moment it's on the merge, it's going to show where that was one frame ago. So let's take a look now. Frame 1, the sphere is there. Frame 2, the sphere is moved. And it's now merged the moved sphere from this transform with the sphere as it was on frame 1. Now frame 3, it's showing frame 2, which was these two, and the current frame 3, which is this new one. So as we play through, it's basically going to leave a trail behind of all the spheres. So hopefully that kind of makes sense. So yeah, basically we're just adding, whatever's going into input 1 to whatever it was showing the previous frame. So it's just accumulating things every single frame. So yeah, as you can see, like operating on the data that already existed rather than kind of calculating afresh. And just one other thing to note, if you've never used a solver before, is we have this blue bar down here. Pretty much that just means that it's caching out the solve. So pretty much it doesn't really matter here. I can click way up here, it's going to calculate instantly, and that's no problem. But suppose we had some really complicated things going on inside the solver, and it took maybe 3 or 4 seconds to calculate every single frame. So it took maybe a minute to calculate the first second of footage. Then instead of having to wait a whole, another second every single time we want to, 3 or 4 seconds every time I want to watch these frames, now they're cached, now they're blue. So it just will save it into the memory and allow us to scrub through it freely. And also it means, we can play through and then also scrub backwards. In some programs like Maya or whatever, you can play forwards, but then you can't go backwards. You've got to go all the way back to the beginning and reset the whole thing. If we were to change something about the simulation, so I'm just going to swap the inputs of the merge with, let's just go up here, with a Shift R. You can see now it turns orange. And that pretty much means that the cache is still saved to memory, but it's no longer accurate. It no longer reflects the information that is, the settings that are currently inside the solver. So, at the moment the merge, doesn't matter which way the inputs go in, that doesn't matter. But the point is something in here has changed. So Houdini's basically gone nope, that cache is no longer accurate. I'm a be orange now until I go back to the beginning. And then play through again. Now it plays through with the new settings, it's blue again. And just one last thing about the solver before we move on is if we scrub through here, you can see the circle's kind of not leaving a trail now. And the reason for that is because we're inside the solver. That is just something that will probably confuse you if you don't know about it, is you've got to just make sure to go outside of the solver. Go take it back, hit reset simulation to clear that bar. If you go inside the solver, it's just going to, not show what's actually happening. But as soon as I go out, it'll show it. So yeah, that's just kind of weird glitch about it. You just have to make sure do all your changes in here, but then go back outside to see what's actually happening. So anyway, yeah, that was a bit of a tangent. Hopefully that kind of explains how the solver works. So I'm basically going to take our solver with the merge and just chuck it into our lining here. And you can see the circles are still there because it's still cached, even though, there's a different thing plugged in now. So we're just going to go back to the beginning, and now it'll recache. So straight away you can see, instead of, up here, we've got our bolts kind of flickering around. Now our bolts are, just pressing the wrong buttons there, the bolts are persisting. So pretty much every time one is created, it stays there forever because it gets merged with the previous frame and it gets remembered by the solver. And you can see actually if we scrub through the first, say, like 8 frames, like nothing happens, right? Everything looks the same. But if we go to the geometry spreadsheet, check out, I'll just order this by point number. So there, we've got 23 points. Go ahead a couple frames. Now 47 points. Now 71 points. Even though, nothing's actually moving in this time, what's happening is it's merging the previous frame, starting with these points, with the same points again. So pretty much we just have the same line being duplicated for every single frame that it is going into the solver. So there we go. It doesn't change until, way up here after a second. So for the first second, we're pretty much just having like constant duplicates of these lines being created. If I turn on point numbers, you can kind of see like there's some overlapping numbers there, and they keep going up, even though, it's the same line there the whole time. So pretty much the way to solve this is we want the bolts to be in a different position on every single frame, so we get no overlap. So we can do that by going up to our scatter here, and we had this expression for the global seed, which would basically make the bolts jump around, every so often, and we're just going to delete that. So I'm going to hold Control Shift and click on the word global seed. So I'm just going to type in here $F, so current frame. So now if we just look through before the solver, the bolts are pretty much changing to a different place on every single frame. So if we look through the solver, you can see, those are all going to get added together. But now we're not getting any overlap, like it's scattering to a new point every single frame. So, this is pretty hectic at the moment. If we look through the end, like, let's turn up numbers there. This is getting pretty crazy right there. It's like, yeah, getting laggy and stuff too. This probably isn't what you want. So what we're going to do is try and make these bolts spawn in kind of controllably over time. So basically we have our wrangle here, and this is controlling how often they move around and how many there are at a time. So, we can go down to some of the settings we made, our bolt count, bring this down, so, maybe it's just like 1 bolt at a time. It's a bit more sensible, but, it still gets pretty crazy. So I think I'm going to just get rid of this. And copy 2, like we don't need that. And I'll just plug that in there. So now we just have our add going into the copy. And you can see everything's disappeared. So also I'm just going to look through before the solver, just for now. So everything's disappeared, and that's because our scatter is currently looking for this rand count parameter in the copy stamp. And if we look at the copy, the rand count is looking for a @BoltCount attribute. And that was created by the wrangle, and since we no longer have the wrangle, it's just kind of reverting to 0 and, scattering 0 points. So that's the first thing we need to do, is make a wrangle to control this. Well, a VOP actually. Yeah, I think I'm going to do this with a VOP. Like, you can do it both ways, and in the scene file for, the end of this, I'll share, it will have like the VOP method as well as the wrangle method. But yeah, just for the tutorial I'm going to use a VOP just because I think it's kind of visual and hopefully it makes more sense like watching it as a tutorial. So yeah, let's just check, what was a bolt count? So we can get rid of bolt life, get rid of rand spawn, and I'll just cut and paste that in there, and cut and paste. And again, just Control-Shift-Click. You can see it's still green, even though there's nothing written in there. That's because it's still kind of in expression mode. So just Control-Shift-Click and it will go back to normal. And then just click that to set that back to default. So yeah, the first thing we need is a bolt count attribute. So I'm just going to dive inside the VOP here. And first thing is make a bind export. And we'll call this bolt count. And just to start off, I'm just going to make it a constant. So I'll just hold middle mouse click constant and set it to 1. So there we go. Now I've got 1 bolt, which chomps all around the place. And so what I think we want to do is have some way to make this bolt only appear, so many times per second. Like with a pop network, we have, so many particles emitting per second. So I want to have so many bolts emitting per second. So let's see if we can find a way to do that. So what I'm going to do first is create a random. And I'm just going to plug the result of this into color. And for the input, I'm going to plug in frame. So frame is pretty much the current frame, like as an integer. So now if we look at the geometry spreadsheet, the color is, some random amount based on the current frame. Also, I'm just going to look through, you can see sometimes this orange bar kind of goes up, even when you're like not looking through the solver. And, if you go back to the beginning, it doesn't, kind of clear. So when that happens, you've got to press the back button, and that'll clear it out. So yeah, anyway. So you can see now I've got the color is a random number. And this is exactly the same as the rand function in a wrangle. It's just going to take some seed, whatever we plug into it, and based on that generate a random number between 0 and 1. So as you scrub through, you can see for color, our number is changing to different random numbers between 0 and 1. And let me just make this a little bit bigger. Just it gets pretty humongous with Vex. I'm just going to hit D as well and change this to rounded. So make it a bit neater. Nope. Wait. Rounded. Bezier? Rounded. I broke it. Let's see. New network view. Lightning effects. Point bop. Rounded. There we go. That's the sweet stuff. Alright, yeah, sorry about that. So, we've got our random number between 0 and 1 for every single frame. Now the next thing I'm going to do is multiply that by a constant. So again, I'll just hold middle mouse click on this input and let go, and it'll create a constant. And the value of the constant, I'm going to set to a little thing called $FPS, which is the global variable for frames per second. So, you could just do 24, but this pretty much means we can change, the frames per second, and it should still work perfectly. So now instead of a random number between 0 and 1, we have a random number between 0 and 24. So the next thing, I'm just going to add... in fact, no, I'm going to add constant. And put that there, and just leave it on 1. So whatever number it was, we're just going to add 1 to it. And you'll see why in a sec. We're going to make a float to integer. So the float to integer is the same as the int expression that we used in a wrangle before. So it pretty much rounds down to the nearest whole number. So you can see from the add constant we have 16.9, and then we use the float to integer, which gets rounded down to 16. So yeah, that's why we added the 1. So now instead of having rounded down a random number between 0 and 23, we now have a whole number from 1 to 24. So you can see as we scrub through, well, this number will just change. Like there we've got 24, like sometimes down to 1. And so it'll just be a random thing every single frame. Okay, so the next thing I'm going to add is a little loop. So I'm just going to type if and make this if block. So we'll just put that there. And so the if block pretty much has this kind of like bubble around it that just encompasses whatever's in the block. But that doesn't matter. We're not going to use the end either. We're pretty much going to use the begin for this. So the way it works, we'll make a compare, and the compare will plug the result of this float to integer in. So the compare is basically going to take our input 1 and then compare it to input 2. And then the result is Boolean, so either true or false. Or in other words, it'll either be 0 or 1. So the test at the moment is equal. We're going to make it greater than. So is this value from our float to integer greater than whatever's in input 2? So for this, I'll just make another constant, and for now, just like set it to 10, say. And then so the Boolean can go into the condition for the if loop because that accepts a Boolean. So that pretty much just means, if this condition is true, if this number is 1, then the if loop will occur. Or, if the condition is not true, then the if condition will not occur. So inside here, we're going to make a remove point. And by default, the point number is -1 because, there's no point -1. It starts at 0. So we could either plug in our global at ptnum variable into here, but since we only have this one point going in, we can just say 0. And there, you can see our point was deleted. So that's pretty much what the remove point does. It will delete a point based on this loop. So yeah, let's just go over this. So basically here we have a random number between 0 and 1 is picked every single frame. And then that's multiplied and has 1 added to it, so that it becomes a random number between 1 and 25, and then gets rounded down to the nearest whole number, so any integer from 1 to 24. And then we're comparing that. Is that number that it's randomly chosen greater than 10? And if it is greater than 10, then it's going to get deleted. The point is going to be removed. Or if it's not greater than 10, it remains. So you can see as we scrub through, now, some frames, the point gets deleted, and it's no longer there. Or other frames, the value is less than 10, so it remains. Or, less than or including 10. So pretty much my theory here is that if we randomly pick, 10 out of every 24 frames for this point to not be deleted, then that's going to give us roughly 10 things, 10 bolts being spawned every single second. Now, in reality, that's not exactly how the random works. Like, it is truly random. So, 1 second we might have, like 15 frames being spawned. Or the next we might have like 4 or 5 being spawned. But overall, like the ultimate average should be roughly, 10 bolts a second now. So if we jump out and take a look through the solver, we can see now, they're kind of being spawned. If we change this down to like 1 per second, now let's have a look. There we go. 4 seconds in, and we've got 4 or like 5 bolts spawned. So yeah, not perfectly accurate, but it's kind of like probabilistic. So just to give us a little more control over that, let's also change the seed. It'll give us a controller for the seed, so I'm just going to add to this a parameter. And I'm just going to duplicate this parameter actually. So the first one we're just going to call bolts per second. And then this number 2 we're going to call rand seed. So the bolts per second I'll chuck in instead of this constant here. So this pretty much, the parameter just means it'll like appear outside the bop. And then for this rand seed, I'm going to plug it into this add. And just one other thing I'm going to do with it, I'm just going to multiply constant here by just say like 1138 is a really good number. So basically what's happening there is I'm adding some amount to the random seed before, you know, the random number is chosen. And the reason I've multiplied it by, you know, a whole bunch is because if I add like 1 or 2, then, you know, it's like adding 1 or 2 to the frame number. So it'll be like, instead of happening on frame 1, it'll now happen on frame 3, sort of thing. It's like offsetting it in time, if that makes sense. But by multiplying it by, you know, some huge number, now every time we change the seed, it's going to get, you know, drastically changed, like offset by more than the whole time slider sort of thing. So yeah, let's just jump out now and bring this down a bit. So now I have this bolts per second and rand seed. So we'll set this to, you know, 5 bolts per second. So there we go, our bolts are kind of spawning now, and we can just change the seed to make something different happen if we don't like the way that that's looking. So yeah, this is not a perfect controller for bolts per second, but over time it should like average out to be, you know, roughly correct. So the next thing we're going to do is make this work kind of like how particles work. So particles basically use this life attribute and this age attribute. And that's why they turn up in the kind of global variables here, because life and age are, you know, common ones for particles, and they'll totally suit our purposes here. So I'm just going to make another bind export. And this one's going to be age. And just copy paste that, and this one's going to be life. Okay, so the way that age and life works, age starts at 0, and as the thing lives for longer and longer, then the value for age goes up over time. Whereas life is a random number, you know, in the case of, say, particles, that is chosen when the thing is created, and once age reaches life, then it dies. So, you know, it's kind of like destined to only live for whatever the value is for life. So I'm going to make a constant here and leave it on 0 and plug it into age, because age will start on 0. And then for life, I'm just going to do something pretty similar to what we had up here. So I'm going to take our frame, plug it into a random. So let's see, frame, random. And then I'm just going to make a fit range here. So, sorry, it's lagged up a little there. So I'll just plug this random output into the value for fit, and then the result into the bind for life. So let me just go over what's happening here. So the fit will basically take our input value, and then between a range of 0 and 1, it will remap that to, at the moment, a range from 0 to 1. So say our random number was 0.5. And whoops. And then for the fit, we'll set this to, you know, 0 to 100. So our input number is 0.5, and in a range from 0 to 1, we're remapping that from 0 to 100. So our 0.5 would become 50, because it's half of that. If our starting number was 2, then it would get clamped down to 1, and then would get remapped up to 100, if that makes sense. So yeah, pretty much now we just have our random number, which is between 0 and 1, and it's getting remapped to between these two values. And for those two values, I'm going to create 2 more parameters. So this one is going to be called life min, and we'll plug that into destination min, and copy paste, and this one will be called life max. And we'll plug that into des max. So now our thing is going to randomly, you know, have a life given to it for every single bolt, and that life is going to be between this minimum amount and this maximum amount. So let's just take a look at our solver now. Oh, and also we'll just set, so life min, we'll make it say 1 and say 3. And and one more thing, in the copy we need to tell it to apply those attributes to, you know, whatever it's copying. So we need to go up to this attribute tab and just go use template point attributes, and we don't want alpha or blah blah blah, any of that, little of that. We just want age. Actually, yeah, we can delete the whole thing. And life. Oops. Life. And they're the only attributes you want to stamp on. So there we go. Now we've got age and life. And as we scrub through, if we look through the solver, you can see now our age is 0 for everything, and our life is some random amount. And it'll come in pairs because we've got, 2 points per each bolt, like one at the top, one down the bottom. And just one other thing which I noticed with this, sorry, I should have thought this before. Take a look here. We need to add some arbitrary amount to this random here. Because just something I noticed when I was doing this earlier, if we have nothing for this seed, so let's just turn this, rand seed down to 0 now. Then pretty much, nothing's being added here, so it's pretty much as if the seed for this random is frame, and the seed for this random is also frame. So these are always going to produce the same result. And since over here we're doing some stuff and then deleting the highest values, so any values which are higher than this amount are being deleted, then that means the highest values for this are also going to be deleted for life. So if we take a look here through the solver, so our max life at the moment is 3. If we look through the solver, like nothing is going to get anywhere near 3. Like it's all, 1.4 is kind of the biggest number we get. And that's because it has the same random seed. So just a solution for that is I'm just going to make a multiply constant here and multiply it by the meaning of everything. Just some arbitrary amount just to make sure that the amount going into this random is different to the amount going into this random. So now if you have a look through the solver, just reset that. Now we are getting, some large values. Like, we can get all the way up to 3 sometimes. So yeah, just something to be mindful of. So anyway, let's move on. So we've got kind of our age and our life set up, being created onto every bolt now. Now we want the age to kind of increase over time, and then for the points to be deleted once age reaches life. So the way we can do that, if we jump into our solver, I'm just going to make another point VOP. And the thing about a point VOP inside a solver is it's going to obviously operate on the thing every single frame. So, say we're adding 10, then it's going to add 10 to the thing every single frame, rather than, just making it 10 bigger. It's going to, increase by 10 over time. So I'll just show what I mean by that. So I'm just going to take age, and I'm going to bind export age. So age is going out into age. And I'm just going to add a little bit to it. So I'm going to add, whoops, not over there, sorry, add, and then the amount I'm going to add is 1/24th. Because I basically want every 24 frames, I want the whole thing to go up by 1. So 1 second. So I'm just going to make a divide. And I make a constant for the first input, and that will just be 1. And I'll make a constant for the second, and that will be, again, $FPS. So now we have 1/24, and we're going to add that to it every single frame. So let's just jump back out of the solver, because again, while we're inside the solver, because right now we're inside a VOP inside the solver, it's not going to update properly. But if we jump out and reset this, so now you can see age is going up constantly. By 1/24th. So, after 1 second, our age is, like nothing spawns on the first frame. But let's just find a seed where it does spawn on the first frame. So, blah, 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 seed. So now we go up to 24 frames. So that it is now 1 second old. So our largest value for there is 1. So let's dive back in here. Dive back in here. So again, we want to make a little if loop with remove points. So now we're going to compare the age to life. So let's make another compare. And I'll grab our global variable for life, and I'll plug that into the first input. And then I'll grab age, our resulting age, and plug that into the second input. And so our compare is going to test is this number less than this number. And then we'll make an if loop, or an if block rather. Plug the boolean in, and then remove point. And the difference here is because now we have like a whole bunch of random point numbers, we can't just say, delete point number 0. We needed to delete the point that it's currently operating on, if that makes sense. So I need to get our ptnum, where is it, here, and plug that into the ptnum for the remove point. So basically you can tell it, if this condition is true, delete a specific point. And, if you plug in pt number, then it's going to delete the point that is, larger than the value. And I'm also just going to move this down so we're not kind of crossing the streams there. So yeah, hopefully that makes sense. So now age is increasing over time. We're bind exporting it there so that it gets remembered and, the updated one gets reread at the beginning of every frame. And then every frame we're going to compare it. Is this number less than life? And if it is less than life, then it will get deleted. I think I might have this around the wrong way, actually. Let me just test this out. Nope, that is around the right way. So yeah, you can see now, it kind of life goes up. Once this number becomes bigger than, so 2.45 whatever becomes bigger than 2.98 whatever, then it disappears. So let's switch our bolts here. So they're kind of like living for a bit and then dying for a bit. So that's pretty cool. I'm just going to go in here and create a new value. So I'm just going to make another bind export. And then this one is going to be called energy. I basically want it to be kind of representative of how long the bolt has lived for. How much energy it's kind of accrued over its lifetime. So just to kind of demonstrate this, I'm just going to make a divide. And if I put age over life, and I'll just put that into energy, you can see as we go along, energy, oh yeah, I've got to go out of the thing to make it happen. Energy is going to start off at 0 as it lives, and then will end up as 1. Or, won't quite make it to 1, but it'll end up as, 1 like right before it dies. For every single thing. And this is okay, but it means that every bolt is going to always reach 1 energy. If that makes sense. Because it's age over life. And I don't want every single bolt to reach the maximum amount of energy. Like, it should, if it lives for the full 3 seconds, like that is when it will reach the maximum amount of energy. But suppose this bolt only lives for like 1 second, I don't want it to get all the way there. So instead of doing age over life, I'm going to do age over the maximum amount that life could possibly be. So I'll disconnect that. So how can we get that? We'll make a constant. And we'll plug that in there. And I'm just going to jump out and go to our point VOP here. And for our life max value, I'm just going to right click, copy parameter, go into our solver, go into the point VOP, and then for this constant, right click on the value and paste copied relative references. And I'll just say this is constant name max life. So there, now we can see if we take this back, now energy goes up, but it never quite reaches, the full like 0.9, like almost 1 value. Like some bolts will, if their life is, this one's almost 3, it's almost the maximum amount. But other bolts where it's, its life's only, 1.5, its energy value is only going to reach about 0.5 before the bolt dies. Great, so we'll take a look back in the scene view here. So now we have this energy value, which kind of like increases over the life of the bolt, and we can use that to control the color. So I'm just going to grab the color from up here and put it after the solver. And we'll look through it. Just going to reset that there. Scrub ahead a bit. And so for the color type, instead of constant now, I'm going to change it to ramp from attribute. And the attribute is going to be energy. And so you can see now the bolts kind of start off black and become white over time, because we have this black to white gradient. So we'll just change this to like purple, make the other end kind of like blue, and then make that like a heaps white kind of blue. And then over here, just make it like straight up blue, darker kind of, you know, and we will bring kind of like darker violety kind of color in there. And we'll see. Yeah, there we go. So now we have our bolts basically changing color over the lifetime based on that energy value. And so yeah, you can see along with the energy value, like some bolts will make it all the way to like almost that perfect white color, but other bolts will die off, you know, before they even stop being purple almost, because the energy doesn't reach the maximum value for every single bolt. Like sometimes they disappear before then. So let's just take a look through the end. So we've got one last thing to do, is control the turbulence with that. So I'm just going to dive inside the point pop here. And so this is where we had our three kind of levels of noise controlling how turbulent the lightning is. So I'm pretty much going to, I might just make some more room here first actually. Just going to grab this, move it over a bit. So we're going to make a bind. And again, bind in our energy attribute. And then we're going to grab our noise and add a multiply to each one. So I'll paste that there, paste that on the medium noise, and then put this one on the small noise. So yeah, I'll just kind of space these out a bit better. And then our energy, I'm going to plug this into the multiply for each one. So you can see now when energy is 0, like our noise gets multiplied by 0, and the line becomes completely straight. Now I think this is a little too much at the moment, so I'm going to make a clamp. And so the clamp's just going to keep it between a certain range. So I'd say for the large noise, I do want to multiply by, you know, 0. Have like no large noise at the beginning of the bolt's life. But for the medium noise and the small noise, I'm just going to, sorry, it's getting a little messy here. So yeah, energy multiplying by the large noise, you know, before the noises get added together. And then for the medium noise and the small noise, I'm going to multiply it by this clamped energy. And the clamp is going to be from, say, 0.3 to 1. So instead of the smallest value being 0, the smallest value will be 0.3, and then it will go up to 1 over the lifetime. Let's have a look at that. So there you go. Now our noise is kind of getting wigglier over time. And I might even just increase the maximum amount of noise for these. So like the medium amplitude, maximum maybe like 2.5. The large noise, I'll make it say 3.75, maybe even 4. And the reason is because, you know, that is the maximum value now. Like most bolts like won't even reach that amount. It's only like the few that live for the longest amount of time where it'll even get that turbulence. So let's play through that. So yeah, there we go. So yeah, that is pretty much how you can use the solver to create evolution of the bolts and make a lightning solver. So I hope that was helpful. Again, feel free to message me or whatever if you have any questions. And stay tuned for next time where I'll be going over some rendering and compositing of this effect. So yeah, thanks for watching.